International System of Units. Before consensus was reached internationally on the system of units which were to be followed by all countries, several different systems were adopted by countries. Some countries followed the CGS system of units. This system had the base units for length, mass and time as centimeter, gram and second respectively. Another system of units used was the MKS system, which had the base units for length, mass and time as meter, kilogram and second respectively. The system adopted by the British was known as the FPS system, standing for foot, pound and second respectively. All these systems were eventually replaced by one standard system, followed by the entire world, known as the SI system. SI is an abbreviation of Système International d'Unité, which means International System of Units in French. This system was developed at the General Conference on Weights and Measures in 1971. All SI units follow the decimal system, unlike other systems of units. This makes conversions within the system easier. The SI system is made up of 7 base units. These units are shown in the table above. The SI unit for length is meter, which is the distance traveled by light in vacuum in a time interval of 1 by 299,792,458 of a second. The SI unit of mass is kilogram, which in turn is the mass of the international prototype of the kilogram kept at the International Bureau of Weights and Measures in Sèvres, France. Time has the SI unit second, which is the duration of 9,192,631,770 periods of radiation, corresponding to the transition between 2 hyperfine ground levels of the cesium-133 atom. The SI unit of current is ampere, which is that constant current which, if maintained in 2 straight parallel conductors of infinite length, of negligible circular cross-section, and placed 1 meter apart in vacuum, would produce between these conductors a force equal to 2 × 10⁻⁻⁷ Newton per meter of length. Temperature has the SI unit Kelvin, which is the fraction 1 by 273.16 of the thermodynamic temperature of the triple point of water. Amount of substance is measured with the SI unit mole, which is the amount of substance of a system which contains as many elementary entities as there are atoms in 0.012 kilogram of carbon-12. The SI unit of luminous intensity is candela, and is defined as the luminous intensity in a given direction of a source that emits monochromatic radiation of frequency 540 × 10⁻12 Hz, and that has a radiant intensity of 1 by 683 watt per steradian in that direction. In addition to these 7 base units, we define radian as the SI unit for a plane angle, and steradian as the SI unit for a solid angle. An angle of 1 radian is obtained in an arc with a length equal to the radius of the circle. Similarly, a steradian is defined as the solid angle subtended at the center of a sphere of radius r by a portion of the surface area of the sphere whose area A equals r squared. All measured quantities have units which are derived from these base units. This means that all other units of measurement that we encounter are a combination of these fundamental base units. Of mass. Mass is a fundamental property of matter and is independent of factors like temperature, pressure, or location of the object in space. Its SI unit is kilogram or kg. 1 kilogram is the mass of the international prototype of the kilogram, maintained at the International Bureau of Weights and Measures in France. A copy of this prototype is kept at New Delhi at the National Physical Laboratory, NPL. When we attempt to measure masses of atomic particles, we find that the kilogram is a very inconvenient unit. Instead, we use the Unified Atomic Mass Unit. 1 unified atomic mass unit equals 1 U equals 1.66 into 10 raised to minus 27 kilograms. Measurement of time. As the basis of time measurement, we now use atomic clocks to provide a precise idea of time. Atomic clocks make use of periodic vibrations of the cesium atom. A second is the time taken by the cesium-133 atom to execute 9,192,631,770 vibrations between two hyperfine states. Cesium clocks are used because they are extremely accurate. In a year, the amount of time by which the cesium clock might stray is no more than 3 µs. One such cesium clock is maintained at the National Physical Laboratory in New Delhi, when the distance to be measured is extremely large. For example, measuring the distance of a star from Earth cannot be done using a meter scale. For measuring such large distances, we make use of what we know as the parallax method. Let us first find out what parallax is. Hold a pencil in your hand and look at it with one eye closed. Now look at the pencil through the other eye. Did you notice an apparent change in position of the pencil? This apparent change in position of an object with change in perspective from which it is observed is known as parallax. The distance between the 2 points of observation is known as the basis, which in this case is the distance between the eyes. In order to measure the distance of a planet from Earth, we observe the position of the planet from 2 different points on the Earth, separated by a known distance. We then measure the angle between these 2 directions along which the planet was observed. This angle is known as the parallax angle or the parallactic angle. The distance between the planet and each of the points of observation is much greater than the distance between the 2 points. Therefore, the ratio of the distance between the 2 points of observation and the distance between the point and the planet is much less than 1. The parallax angle, therefore, is very small. The 2 observatories on the Earth, therefore, may thus be considered to be forming an arc of a circle, whose center is the planet being observed. The distance between these observatories is, therefore, given by the product of the distance to the planet and the parallax angle. Distance to the planet, therefore, is the distance between the observatories divided by the parallax angle. We can also determine the diameter of the planet we are observing by a similar method. We can measure the angle subtended by the edges of the planet at the same point on the Earth. Since we already know the distance to the planet from the Earth, we may then find the diameter of the planet to be the product of the angle subtended by its edges and the distance to the planet from the Earth. Estimation of very small distances. Size of a molecule. For measuring small distances, we make use of specialized instruments like the screw gauge. However, when distances at the molecular level have to be measured, we need to make use of special methods instead of instruments. One such method is used to estimate the size of molecules of oleic acid. Oleic acid is a soapy liquid with a large molecular size in the range of 10 raised to minus 9 meters. To measure the size of the oleic acid molecule, we first form a monomolecular layer of it on water. To do so, we dissolve 1 cc of oleic acid in alcohol to form a solution with the 20 cc volume. We then take 1 cc of this solution and dilute it again in alcohol to obtain 20 cc of solution. The concentration of oleic acid in the solution is now 1 by 20 into 20 centimeters cubed of oleic acid by centimeters cubed of solution. We then sprinkle some lycopodium powder on water, which is contained in a large trough. On this, we put 1 drop of the oleic acid solution we made. The oleic acid drop spreads into a uniform and roughly circular film of molecular thickness. We then measure the diameter of the film to get its area, denoted by A. Let us assume that we have put n drops of the solution into the water. The volume of n drops then becomes NVCC. The amount of oleic acid in this solution is NV by 400 cc. The oleic acid spreads out to form a layer of thickness T, and the area of the film is A. The thickness of the film is then given by T equals volume of the film by area of the film, or T equals NV by 400 cc. If the film is of monomolecular thickness, then the thickness of the film gives us the diameter of the oleic acid molecule. Precision of instruments and errors in measurement. Whenever measurements are made, there always is some amount of uncertainty in the obtained result. This uncertainty is known as an error. When talking about errors in an instrument, we need to define two terms, accuracy and precision. Accuracy is a measure of how close the measured value is to the true value. Precision is a measure of the resolution to which the quantity is measured. For example, let us attempt to measure the length of an object. Its true length is 6.589 meters. Measuring the length using one instrument gives us 6.4 meters. A second instrument gives us the reading 6.38 meters. Obviously, the first instrument is closer to the actual value and hence is more accurate than the second instrument. However, we see that the first instrument has a resolution of 0.1 meters, while the second instrument has a resolution of 0.01 meters. Thus, the second instrument is more precise than the first one is. Errors can be classified broadly into two categories, systematic errors and random errors. Systematic errors are errors which tend to be in one direction only, either the positive or the negative. Systematic errors may occur as a result of imperfect calibration of the measuring instrument. For example, improper calibration of a thermometer may result in it showing the temperature to be greater than 100 degrees at the boiling point of water. Such errors are called instrumental errors. Systematic errors may also occur due to incorrect experimental techniques. For example, placing a thermometer in your armpit always gives a lower value of temperature than the actual temperature of the body. Systematic errors may also occur due to incorrect handling of the instrument by the user. For example, measuring temperature under an air conditioner will never give us the correct value of temperature. Random errors, on the other hand, are true to their name, random in nature. They may occur due to a fluctuation in experimental conditions and hence are difficult to predict. When random errors occur, multiple readings of the same observation may give us different values. Least count error is another kind of error which depends on the resolution of the instrument. Least count of an instrument is the smallest value that can be measured by that instrument. Least count error occurs because of differences in precision of different instruments and may be reduced by using instruments which are more precise in nature. Absolute error, relative error, and percentage error. The magnitude of the difference between the true value of the quantity and the individual measurement value is called the absolute error of the measurement. Since the true value of the quantity may not always be known, it is assumed to be the arithmetic mean of several observations of its value. The difference between the true value and the individual measurement may be positive or negative, but the absolute error is always positive in nature. The arithmetic mean of all the absolute errors is taken to be the final or the mean absolute error of the physical quantity. The relative error is the ratio between the mean absolute error and the mean value of the quantity being measured. When this ratio is expressed as a percentage, then the error is known as percentage error. Combination of errors. When two quantities are added or subtracted, the absolute error in the final result is the sum of the absolute errors in the individual quantities. For example, let Z be a combination of two quantities, x and y. Z equals x plus y. Z plus or minus delta Z equals x plus or minus delta x plus y plus or minus delta y. maximum possible error is delta z equals delta x plus delta y. For the difference z equals x minus y, z plus or minus delta z equals x plus or minus delta x minus y plus or minus delta y equals x minus y plus or minus delta x plus or minus delta y, or plus or minus delta z equals plus or minus delta x plus or minus delta y. When two quantities are multiplied or divided, the relative error in the result is the sum of the relative errors in the multipliers. Thus, when two quantities are being multiplied, the maximum relative error is delta z by z equals delta x by x plus delta y by y. The relative error in a physical quantity raised to the power k is k times the relative error in the individual quantity. Thus, if z equals u raised to p v raised to q by w raised to r, delta z by z equals p into delta u by u plus q into delta v by v plus r into delta w by w.
Significant figures. Measurements, like we have seen, are prone to errors. It is hence important to report the results in a manner that would indicate the precision of measurement. A reported result includes A. Digits in the number that are reliably known, and B. The first digit that is uncertain. Together, they are known as significant digits or significant figures. Let us take a pendulum as an example. If we say that the period of its oscillation is 1.54 seconds, the digits 1 and 5 are the reliable numbers and 4 is uncertain. Here, the measured value has three significant figures, 1, 5, and 4. Similarly, in an object that has been measured to be 267.5 centimeters, number of significant figures is 4. Here, 2, 6, and 7 are certain digits, whereas 5 is uncertain. Reporting more digits than the significant digits can be misleading. It would give you a wrong idea about the precision of the measurement done. There are rules to determine the number of significant figures. Since it is about the precision of measurement, it depends on the least count of the measuring instrument. A choice of change of different units does not change the number of significant digits or figures in a measurement. The following observations make this clearer. Let us take an example where the length of an object is 2.508 centimeters. It has four significant figures, 2, 5, 0, and 8. But for different units, the same value can be written as 0.02508 meters, or 25.08 millimeters, or 25080 micrometers. In all these numbers, the significant digits 2, 5, 0, and 8 still remain 4. The placement of the decimal point is of no consequence here. From this example, we can obtain the following rules. All the non-zero digits are significant. All the zeros between two non-zero digits are significant no matter where the decimal point is, if at all. If the number is less than 1, the 0 or zeros on the right of decimal point but to the left of the first non-zero digit are not significant. Here, in 0.002508, the highlighted zeros are not significant. The terminal or trailing 0 or zeros in a number without a decimal point are not significant. Thus, in 158 meters equals 15,800 centimeters, 1,58,000 millimeters has only three significant figures, 1, 5, and 8. The trailing 0 or zeros in a number with a decimal point are significant. For example, numbers 3.800 or 0.04500 have four significant figures each. This leads us to another set of observations. Trailing 0 or zeros can be confusing. Let us take an example where the length of an object is reported to be 5.800 meters. One can say that it could simply be written as 5.8 meters. But it must be remembered that zeros here are meant to convey the precision of measurement and hence are significant. Now suppose the units were changed. 5.800 meter equals 580.0 centimeters equals 5800 millimeters equals 0.005800 kilometers. In such cases, keeping the first set of observations in mind, one might erroneously decide that the number has two significant figures, 5 and 8, where actually there are 4 significant digits. Change of units cannot change the number of significant figures. To remove such ambiguities in determining the number of significant figures, the best way is to report every measurement in scientific notations in the power of 10. In such notations, every number is expressed as a into 10 raised to b, where a is a number between 1 to 10 and b is any positive or negative exponent or power of 10. To get an approximate idea of the number, we may round off the number a to 1 for a less than equal to 5 and to 10 for a greater than 5 and less than equal to 10. Thus, the number can be expressed approximately 10 raised to b, in which the power b of 10 is called the order of magnitude of physical quantity. When we seek only an estimate, the quantity is of the order of 10 raised to b. For example, diameter of the earth is 1.28 into 10 raised to 7 meters. It is of the order of 10 raised to 7 meters with the order of magnitude 7. In case of a hydrogen atom, whose diameter is 1.06 into 10 raised to minus 10 meters, it is of the order 10 raised to minus 10 meters, the order of magnitude being minus 10. This means that the diameter of Earth is 17 orders of magnitude larger than the hydrogen atom. One has to write the decimal after the first digit. The confusion we discussed earlier in observation 2 now disappears. 5.800 meters equals 5.800 into 10 raised to 2 centimeters equals 5.800 into 10 raised to 3 millimeters equals 5.800 into 10 raised to minus 3 kilometers. You must remember that the power of 10 is irrelevant when it comes to determining significant figures. All zeros appearing in the base number in scientific notation are significant. There are 4 significant digits here. Scientific notations can be considered ideal for reporting measurements, but it is not adopted. We can follow 2 more rules here. For a number greater than 1, without a decimal, the trailing 0 or zeros are not significant. For a number with a decimal, the trailing 0 or zeros are significant. Look at this example. Digit 0, which is conventionally put on the left of the decimal, is never significant. The zeros at the end of such numbers are significant. Multiplying or dividing factors that are neither rounded numbers nor representing measured values are exact and have infinite significant digits. In r equals d by 2 or s equals 2 pi r, 2 is an exact number which can be written as 2.0, 2.00 or 2.000. In capital T equals T by N, where N is an exact number. Rules for arithmetic operations with significant figures. One must remember that the results of a calculation that involves approximate measured values of quantities, which means that the values have limited number of significant figures, must reflect the incomplete value of the original measured values. The results would always be less accurate than the original measured values. The final results should not have more significant figures than the original data from which it was derived. For example, for an object with mass 5.145 grams with 4 significant figures and volume 3.16 centimeter cube, the density would be 5.145 by 3.16 grams per centimeter cube, which equals 1.628164557 grams per centimeter cube. Here, the value of density is accurate to 9 decimal places. Now, the actual measurements would be much less precise than this calculated value. We don't need to record values to such levels of precision. There are rules to ensure that the final results of a calculation are precise only till the level where they are consistent with the precision of input measured values. 1. In multiplication or division, the final result should retain as many significant figures as there are in the original number with the least significant figures. Therefore, in the above example, density is equal to 5.145 by 3.16 grams per centimeter cube, which equals 1.628164557 grams per centimeter cube. The number with the least significant figures is 3.16, which is 3. So the density should be reported as 1.63 grams per centimeter cube. Second, in addition or subtraction, the final result should retain as many decimal places as are there in the number with the least decimal places. For example, sum of numbers 367.83 grams, 375.3 grams, and 0.643 grams is 943.773 grams. But the number with the least decimal places is 375.3 grams, which is true to only one decimal place. So the reported result should be rounded off to 943.8 grams. Similarly, subtraction of the lengths 0.707 meters and 0.702 meters would be 0.005 meters, which can be written as 5 into 10 raised to minus 3 meters. Rule 1 does not apply here, and values should be written as 944 grams or 5 into 10 raised to minus 3 meters in the above examples, as they are not precise. Remember that for addition and subtraction, the rule is in terms of decimal places. Rounding off the uncertain digits. Sometimes the results obtained with approximate numbers with more than one uncertain digit should be rounded off for convenience. Now, the rule. A number 3.858 rounded off to three significant figures would be 3.86. Another number 3.854 would be 3.85. The rule here would be that the preceding digit is raised by 1 if the insignificant digit to be dropped, the underlying digit in this case, is more than 5 and is left unchanged if the latter is less than 5. But for a number like 3.855, where the insignificant digit is 5, the convention would be that if the preceding digit is even, the insignificant digit is simply dropped, and if it is odd, the preceding digit is raised by 1. Then the number 3.865 rounded off to three significant figures becomes 3.86, and 3.835 becomes 3.84. In intermediate steps in a calculation, one should have one digit more than the significant figures and round it off to proper significant figures at the end of the calculation. Speed of light, that is 2.99792418 into 10 raised to 8 meters per second, a number with many significant figures, can be written as 3 into 10 raised to 8 meters per second. Exact numbers that appear in formulae like 2 pi in t equals 2 pi square root of L by g have infinite significant figures. Value of pi equals 3.1415926 has a large number of significant figures. We assume the value to be 3.142 or 3.14, which is limited significant figures. Rules for determining the uncertainty in the results of arithmetic calculations. To understand the rules that govern the determination of the uncertainty or error in the measured quantity in arithmetic operations, we must look at the following examples. 1. The length and breadth of a rectangular sheet are 18.3 centimeters and 11.2 centimeters respectively. There are three significant figures in each measurement. So length L can be written as L equals 18.3 plus minus 0.1 centimeters, which equals 18.3 centimeters plus minus 0.5%. Breadth B equals 11.2 plus minus 0.1 centimeters, which equals 11.2 centimeters plus minus 0.9%. Using the combination of errors rule, error of the product of two experimental values will be L into B equals 204.96 centimeters square plus minus 1.4%, which equals 204.96 plus minus 3.3 centimeters square, which is LB equals 205 plus minus 3 centimeters square. Here 3 centimeters square is the uncertainty or error in the estimation of the area. Second, if a set of experimental data is specified to n significant figures, a result obtained by combining the data will also be valid to n significant figures. In subtraction, the number of significant figures can be reduced. For example, 14.8 grams minus 5.07 grams are both specific to three significant figures would not be evaluated as 9.73 grams but as 9.7 grams. Uncertainties in subtraction and addition combine in a manner where the smallest number of decimal places in any of the numbers added or subtracted is considered instead of the number of significant figures. Third, the relative error of a value of number specified to significant figures depends not only on n but also on the number itself. For example, for measurements of mass 2.02 grams, accuracy in measurement is plus minus 0.2 grams. Another measured mass, 8.98 grams, is also accurate to plus minus 0.02 grams. The relative error in 2.02 grams would be plus minus 0.02 by 2.02 into 100%, which equals plus minus 1%. Similarly, the relative error in 8.95 grams would be plus minus 0.02 by 8.98 into 100%, which equals plus minus 0.2%. Also remember that intermediate results in a multi-step computation should be calculated to one more significant figure in every measurement than the number of digits in the least precise measurement. For example, if we take the reciprocal of the number 7.68 and round off the figures to the original three significant figures, then we get 0.130. But if we try to revert back, the reciprocal of 0.130 is 7.69, which would cause an error. So we calculate the number to one more significant figure, that is 0.1302, whose reciprocal is 7.68, thus avoiding errors. This justifies...
Convert the following quantities into radians. 10 degrees, 3 arc minutes, 5 arc seconds. Solution. 10 degrees. We have 360 degrees equals 2 pi radians, or 1 degree equals 2 pi by 360 radians. Hence, 10 degrees equals 2 pi by 360 radians into 10 radians equals 0.1745 radians. 3 arc minute. We have 1 degree equals 60 arc minutes, or 60 arc minutes equals 2 pi by 360 radians. Or 1 arc minute equals 2 pi by 360 into 60 radians. Thus, 3 arc minutes equals 3 into 2 pi by 360 into 60 radians equals 8.72 into 10 raised to minus 4 radians. 5 arc seconds. We have 1 arc minute equals 60 arc seconds, or 60 arc seconds equals 2 pi by 360 into 60 radians. So, 1 arc second equals 2 pi by 360 into 60 radians. Hence, 5 arc seconds equals 2 pi into 5 by 360 into 60 radians equals 2.422 into 10 raised to minus 5 radians. To demonstrate the parallax error, a scientist stands at a point P in front of a tower T. Now, he rests his eyes on a very distant object D, which is in line with PT. He then walks up to Q, which is normal to the line PT and at a distance of 75 meters from P. Owing to the extreme distance of D, the line of sight at Q is similar to PD, but the line of sight for T changes by an angle 45 degrees. Estimate the distance PT. Solution. We have phi equals 45 degrees, which is the parallax angle. Now from triangle PTQ, tan phi equals 75 by PT, or PT equals 75 by tan phi, equals 75 by tan 45, equals 75 by 1. Thus, PT equals 75 meters. As given in the figure, the angle theta subtended by a point T on the moon at 2 points P and Q is 1 degree 36 minutes. Given that PQ is the diameter of the Earth and PC equals CQ equals 6.4 into 10 raised to 6 meters. Calculate the distance PT. Solution. Given that theta equals 1 degree and 36 minutes equals 1.6 degrees. As 1 degree equals pi by 180 radians, so theta equals 1.6 into pi by 180 radians equals 0.028 radians. Therefore, PT equals QT equals PQ by theta, or PT equals 2 into 6.4 into 10 raised to 6 by 0.028 meters, equals 4.57 into 10 raised to 8 meters. Given that the distance d of Earth from the Sun is 1.51 into 10 raised to 11 meters, and the angular diameter theta of the Sun is 0.533 degrees, calculate the radius RS of the Sun. Solution. Angular diameter of the Sun equals theta, as theta equals 0.533 degrees. Thus, theta in radians equals 0.533 into pi by 180 equals 0.0093 radians. As we know, ds equals theta into d, where ds equals diameter of the Sun, or ds equals 0.0093 into 1.51 into 10 raised to 11 meters equals 1.4 into 10 raised to 9. Hence, rs equals ds by 2 equals 7 into 10 raised to 8 meters. Example 2.5. Imagine a world where the size of a nucleus, which is in the range of 10 raised to minus 15 to 10 raised to minus 14 meters, is increased to the size of the tip of a sharp needle. What will be the new size of the atoms on this new scale? Assume that the size of the tip of the needle to be of the order of 10 raised to minus 5 meters. Solution. To change the scale of the size of the nucleus, we first find out the ratio of the new scale to that of the old scale. Hence, the new scaling up has to be done to the order of 10 raised to 10. Thus, an atom which has the size of approximately 10 raised to minus 10 meters will be scaled to the size of a circle with a radius of 1 meter. Hence, we can state that the tip of a needle placed in the center of a sphere of radius 1 meter can represent the actual scale of a nucleus in an atom. Example 2.6. Two clocks, A and B, are tested against a standardized clock at NASA as part of the satellite launching routine test. At 12 noon, as shown by the standard clock, the reading for the next 7 days are tabulated as shown below. Which clock should be discarded based on the precision of the time interval measurements? Clock A, clock B. Sunday, clock A, 12 hours 7 seconds. Clock B, 10 hours 15 minutes 9 seconds. Monday, clock A, 12 hours 1 minute 55 seconds. Clock B, 10 hours 14 minutes 48 seconds. Tuesday, clock A, 11 hours 59 minutes 28 seconds. Clock B, 10 hours 15 minutes 21 seconds. Wednesday, clock A, 12 hours 1 minute 14 seconds. Clock B, 10 hours 15 minutes 16 seconds. Thursday, clock A, 11 hours 59 minutes 16 seconds. Clock B, 10 hours 14 minutes 15 seconds. Friday, clock A, 12 hours 1 minute 33 seconds. Clock B, 10 hours 15 minutes 27 seconds. Saturday, clock A, 12 hours 1 minute 11 seconds. Clock B, 10 hours 15 minutes 17 seconds. Solution. The variation for clock A lies in the range of 159 seconds. Also, for clock B, the range of variation is 39 seconds. Even though the average reading of clock A is much closer to that of the standardized clock, the range of variation for clock A is nearly 4 times that of clock B. We should note that the important criterion for good precision in time interval measurements is not the clock's zero error but its range of variation. This is because the zero error can be easily corrected. Hence, clock B will be preferred. Example 2.7. For a simple pendulum, the time period of the harmonic oscillations was measured. For sixth reading, the measurements were 3.45 seconds, 3.58 seconds, 3.29 seconds, 3.32 seconds, 3.48 seconds, and 3.51 seconds. For the given readings, calculate the absolute error and the percentage error. Solution. From the above readings, the average reading of the time period is T average equals 3.45 plus 3.58 plus 3.29 plus 3.32 plus 3.48 plus 3.51 by 6 seconds equals 3.438 seconds. As the resolution of all the readings is 0.01 seconds, we can discard the third digit after the decimal point. Thus, T average equals 3.43 seconds. The error in measurement is 3.45 minus 3.43 seconds, which equals 0.02 seconds. 3.58 minus 3.43 seconds, which equals 0.15 seconds. 3.29 minus 3.43 seconds, which equals minus 0.14 seconds. 3.32 minus 3.43 seconds, which equals minus 0.11 seconds. 3.48 minus 3.43 seconds, which equals 0.05 seconds. 3.51 minus 3.43 seconds, which equals 0.08 seconds. Hence, the average of all the absolute errors is E absolute average equals 0.02 plus 0.15 plus 0.11 plus 0.05 plus 0.14 plus 0.08 by 6 seconds equals 0.55 by 6 seconds equals 0.091 seconds. This can be approximated to 0.09 seconds. Hence, the range of error for the time period of the given pendulum is 3.43 plus or minus 0.09 seconds, which is equal to 3.34 seconds to 3.52 seconds. The percentage error or relative error is delta E equals 0.09 by 3.43 into 100, which is 2.62%. Example 2.8. Given below are the temperatures of two radiating bodies, A and B, as measured by a common thermometer, T. TA equals 350 degrees Celsius plus or minus 4 degrees Celsius. TB equals 410 degrees Celsius plus or minus 6 degrees Celsius. Calculate the difference in temperature and the implied error. Solution. The difference in temperature. Delta T equals TB minus TA equals 410 degrees Celsius plus or minus 6 degrees Celsius minus 350 degrees Celsius plus or minus 4 degrees Celsius. Or delta T equals 60 degrees Celsius plus or minus 10 degrees Celsius.
Example 2.9. In a science experiment, as per Ohm's law, resistance R was calculated with voltage V equals 100 plus minus 1.87 volts and current I equals 10 plus minus 0.23 amperes. Find out the percentage error in R. Solution. We are given that the percentage error in V is 1.87% and that in I is 2.3%. Hence, the percentage error in the calculated resistance will be delta R equals 1.87% plus 2.3% equals 4.17%.
Example 2.10. Given are two resistances RA and RB with their resistances 150 plus or minus 3 ohms and 225 plus or minus 2 ohms respectively. Find out the equivalent resistance Req for both the series and parallel combinations. Use the following relations to calculate the equivalent resistance Req. Series Req equals Ra plus Rb. Parallel 1 by Req equals 1 by Ra plus 1 by Rb. To calculate the percentage error in Req, use the following formula. Delta Req by R square Eq equals delta Ra by R square A plus delta Rb by R square B. Solution. For the series combination, the equivalent resistance Req equals Ra plus Rb equals 150 plus or minus 3 ohms plus 225 plus or minus 2 ohms, or Req equals 375 plus or minus 5 ohms. For the parallel combination, we have 1 by 150 plus 1 by 225 equals 1 by 75 into 1 by 2 plus 1 by 3 equals 1 by 75 into 5 by 6. Hence, the equivalent resistance is 90 ohms, or Req equals 90 ohms. Now, to calculate the percentage error delta Rq in the parallel combination of Rq, we have the following equation. Delta Rq by R square Eq equals delta Ra by R square A plus delta Rb by R square B. Or delta Req by R square Eq equals 3 by 150 square plus 2 by 225 square. Delta Req by 90 square equals 1 by 150 into 50 plus 2 by 225 square. Delta Req equals 90 square by 150 into 50 plus 90 square into 2 by 225 square equals 1.08 plus 0.32 ohms equals 1.4 ohms. Hence, the Req for parallel combination is 90 plus or minus 1.4 ohms. Example 2.11. We have a given formula for a variable x as x equals y cubed t to the power of 1 by 3 by p square q to the power of half. Find the relative error in x. Solution. The relative error in x is delta x by x equals 3 into delta y by y plus 1 by 3 into delta t by t plus 2 into delta p by p plus half into delta q by q. For a simple pendulum stationed at an old tower in London, the time period t is given by the formula t equals 2 pi root L by g, where L equals length of the simple pendulum and assume g as 10 meters per second square. The measured value of L is 25 centimeters with an accuracy of 1.25 millimeters, and the time period t is 1 second with an accuracy of 0.025 seconds. Find the accuracy in finding the value of g. Solution. As t equals 2 pi root L by g, we have square root of g equals 2 pi into square root of L by t, or g equals 4 pi square into L by t square. Hence, the relative error in the value of G is delta G by G equals delta L by L plus 2 into delta T by T. From the given problem, delta L equals 1.25 millimeters equals 0.125 centimeters, delta T equals 0.025 seconds. Hence, delta G by G equals 0.125 by 25 plus 2 into 0.025 by 1 equals 0.005 plus 0.05 equals 0.055. Hence, the percentage error in finding the value of G is 100 into delta G by G equals 0.055 into 100 equals 5.5%. Example 2.13. A solid cube has a side of 5.625 centimeters. Calculate the total surface area and the volume of the cube to appropriate significant figures. Solution. Let us name the side of the cube as S. Hence, as S equals 5.625 centimeters, the total surface area of the cube S equals 6S square. Hence, S equals 6 into 5.625 square centimeters square equals 189.84375 centimeters square. Hence, we will round off our answer to 4 significant digits. S equals 189.8 centimeters square. Now, the volume V of the cube is V equals S cube, or V equals 5.625 cube centimeters cube equals 177.978515625 centimeters cube. Thus, rounding off to 4 significant digits, we have V equals 178.9 centimeters cube. Example 2.14. A rare substance S is found only in the caves of Ajanta. 4.25 grams of this substance occupies 1.9 centimeters cube. Noting the significant digits of mass and volume, find out the density of this substance. Solution. We know that density equals mass by volume. Thus, as in the given problem, there are 3 significant digits in the given mass and only 2 significant digits in the volume. We should express density to only 2 significant digits. Hence, density equals 4.25 by 1.9 grams per centimeters cube equals 2.236 grams per centimeters cube equals 2.2 grams per centimeters cube. Example 2.15. Consider the equation T equals K root of L by G, where T equals time period of a simple pendulum. L equals length of the pendulum, G equals acceleration due to gravity, and K equals dimensionless constant. Determine whether the equation is dimensionally correct. Solution. Considering the left-hand side, LHS of the given equation, the dimension of time period is M0, L0, T1. Considering the dimensions on the RHS of the equation, we have K equals M0, L0, T0, L equals M0, L1, T0, G equals M0, L1, T minus 2. Hence, the dimension of K root L by G equals M0, L0, T0 into root M0, L1, T0 by M0, L1, T minus 2 equals M0, L0, T0 into root M0, L0, T2 equals M0, L0, T1. Thus, as the dimension on both the LHS and the RHS of the given equation are the same, the equation is correct dimensionally.
Example 2.16. The dimensions of energy is M1, L2, T minus 2, and that of mass M is M1, L0, T0, and of acceleration due to gravity G is M0, L1, T minus 2. Which of the formulae for potential energy U given below can you rule out on the basis of dimensional arguments? H stands for the height of the body. 1. M2, G4. Second, M2, G1, H1. Third, 0.5 into M1, G1, H1. Fourth, M plus GH. Solution. For any formula to be correct, an important criteria is that it should be dimensionally correct. Also, only quantities with the same dimension can be added or subtracted. From the above options, we first find out the dimensions of each of the 5 entities and match it with the dimensions of potential energy. U equals M1 L2 T minus 2. 1. M2 L0 T0 into M0 L4 T minus 8 equals M2 L4 T minus 8. Second, M2 L0 T0 into m0L1t minus 2 into m0L1t0 equals m2L2t minus 2. Third, m1L0t0 into m0L1t minus 2 into m0L1t0 equals m1L2t minus 2. Fourth, m1L0t0 plus m0L1t minus 2 into m0L1t0, this cannot be added. Hence, we see that the correct formula dimensionally from the given option is 0.5 into m1 g1 h1. The noteworthy fact is that even if an equation is dimensionally correct, it is not sufficient for it to be correct. There might be a problem with a constant in the equation which doesn't have a dimension. Hence, a correct equation will always have the correct dimension, but not all dimensionally correct equations are correct.
Example 2.17. An absent-minded scientist found out the mathematical expression for time period t of a simple pendulum but forgot to write it and eventually could not recollect the mathematical equation. Luckily for him, he remembered that the time period depended upon the following quantities: length of the pendulum, acceleration due to gravity. Using dimensional analysis, calculate the mathematical expression for the time period of a simple pendulum and assume Kc to be the constant in the equation. Solution: the mathematical relation between the time period, the length of the pendulum, and the